were looking for MOS amplifiers and we are still watched to model the MOS transistor. Last time I drew some figures, one of them I said that in saturation the IDS which is the drain to source current is equal to half VOV square, half beta VOV square, and which shows as if it is not a function of VDS, and we later showed that it is a function of VDS through a lambda term. Okay. However, if you look at this expression, you can see it is like a voltage controlled current source. So a typical amplifier has a schematic diagram, one can, if you wish to say, I put an input AC which is essentially delta input, delta changes of gain. I pass through VCCS, that is VGS minus VT is what we are now looking into, which converts into change in current because this is the current, and this current is then passing through a load which gives me output voltage V out. So essentially a typical amplifier which we are going to use will have a current source which is a function of input, and then it goes through a load to give me an output voltage, and the change in output voltage means AC voltage. So AC voltage by AC input is essentially the gain, that is what an amplifier is likely to do. So the essential part therefore was to get this expression correctly, and also we will like to see whether the load which we always talked about is that really resistive load or there is something else which we can do. We will see little later that typically in the case of integrated circuits there is no resistor as such is employed because of the area it will take. We will show you how much it may, and therefore you use transistor itself as the resistor or equivalent current source. So we will see that means we need to create a current references or current sources. Okay, that is one of the activity of this course. So we will see how to create a good current source. What is the property of a good current source? The impedance across it should be infinite, ideal current source. So how good we reach there, how good, and that is the most important point, and that is the design, because otherwise you can create anything and you will say there is a good current source, but the output impedance across that should be as high as possible, preferably infinite, but infinite is a number which is unknown. So maybe say hundreds of mega ohms, yeah, it is a big number, so we say okay, that is good enough. Okay. So this is the basic idea which we are following and we continue to follow. Now there is some issue which may appear now. We always thought transistor behaves in a very interesting, nice, simple way, but it does not, unfortunately, particularly if there is a short channel device it will be even worse. Even with a long channel we would like to now see what is the equivalent circuit of a MOS transistor which I can employ in circuit designs. So I have figured it out. There are many other issues which I have yet not discussed, and one of the issue which I start with is I assume threshold was constant. Okay. Now in real life this threshold is not really so much constant as I think so, and it has been figured out that if I apply a substrate bias, negative substrate bias, what will happen? You can see from here this is source grounded, drain is plus VDS for a MOS transistor to work, plus VGS which is exceeding VT. Okay. So if I apply minus bias to source substrate junction, so one can see there was already a depletion layer even at 0 bias. If you apply reverse bias it will further enhance. On the drain side it already had a larger depletion because of VDS was positive. With minus VSB it will be VSB plus VDS, so it will be additional reverse bias now available at the drain base substrate junction. So the depletion layer will be even enhanced there. Now two things which is available, one is of course there is an extra depletion charge in the channel, is that clear? There is an extra depletion charge before VGS, there is an extra depletion charge which is available to you. There is another issue which we will look into later. Since the depletion layer changes, what changes in the normal diode? The depletion layer thickness is related to what? capacitance epsilon s by xd. So larger the xd, capacitance will come down, okay. So there is some issue which we will have to take care in circuit design when you say okay, if you have a VSB, the capacitance also is a function of VSB. Now looking at that part later, since the bulk charges in the channel area is increasing, we know the expression which we have written for Vt, which has a term Qv by Cox, phi ms 2 phi f Qox by Cox minus Qb by Cox, okay. That time the bulk charges were essentially because of the VGS, that is what we said, Ex is very large and whatever depletion is occurring essentially because of VGS. But now you have created additional source for depletion charge, which means now Vt will become higher because already there is a depletion. So you have to first remove that to get into a inversion layer, is that clear? Now this essentially means that the new Vt with additional minus VSB sitting there will be Vt 0, 0 bias Vt, which is normally we were considering, gamma times. Now what is this, is the difference I am adding, this is the original plus how much additional Vt contribution will come because of the additional charge available to you. So what is the now the surface potential, VSB plus 2 phi f, because earlier it was only 2 phi f, now there is a minus VSB on that, that is plus for reverse. So VSB plus 2 phi f is the potential now. So psi s is now becoming VSB plus 2 phi f to the power half under root expression we know, okay, minus without this, that means without the VSB. So this additional this terms multiplied by q gamma, which essentially is the part of this xd expression which we wrote there, QB expression which we wrote there, 1 upon Cox twice K epsilon naught QNA, and D means wire out AD means NA for P N channel device, ND for P channel device. So one word one can say. This is a small query for those who are very keen about devices, is NA should be higher than ND for N channel and P channels. NA ND will be equal for P channel N channels, or N channel NAs will be different from P channel NDs. What is your criteria? Do you think something about as the numbers? Which one should have different dopings? For example, I will give a hint that NA ND will not be equal. So which should be higher and which should be lower? NA higher for N channel compared to ND, because we wrote a P channel expression, all terms were negative, okay. So I do not want Vt to be very large negative for P channels, so actually if I reduce NDs, Vt will go down, okay. If I increase NA, that compensation term will be increasing, so Vt will increase actually positively, and in all circuit designs preferably and not necessarily VTN, that is threshold of N channel, is kept as much same as P channel, but in analog this may not be a criteria. In digital CMOS this is general criteria, because of the swing to be equal we always put VTN equal to VTP in digital, but in analog that is not a compulsion and many times I will not do that. So in which case my two devices will have different doping so that I can adjust my VTs independently. Is that point clear? So this VT now has enhanced compared to its 0 bias case, and that should be taken care, because if that is so, we will like to see, of course this expression we will use later, I just want to show that means there is a threshold variation with VSB which is gamma by 2 VSB plus 2 phi f to the power, just differentiate, okay. So we see change in threshold voltage with substrate bias, obviously here is a minus value, plus gamma by 2 VSB plus 2 phi f to the power minus half, that half will come and minus will appear due to differential. So this is one issue which in analog people have to worry. Now this question may be asked in normal technologies which we use, okay, you just write down then I will come, do not read this, just go up to this, we will come back to the second issue little few minutes. So if I am showing you this, in normal, I will come back to this figure again, in normal CMOS which is what digital inverter is using. This is a P channel device, this is an N channel device. What I see there, that the bulk for P channel and bulk for N channel are normally connected to sources, normally connected to sources. But in most circuits these days, because we want to control Vt through bias, what we do, either we leave this separate or at best we ground them. Is that clear? Now if we ground, because that is what control we need, so if we ground it now, you can see that any potential, whenever current pass through this N channel, there will be a potential drop here. The center point, which is your output point, will have a voltage VDS of the lower transistor. This voltage here, whatever is the VD of the lower transistor, is actually VD of the upper transistor also. Is that clear? That means there is a substrate bias between drain side to the ground, because the bulk is grounded. So even if you are not really putting any VSB or VDB, there is a built-in substrate bias is created, which means the threshold of these two transistors will vary even without doing anything. Is that clear? So now one must worry that in real technologies where I am not actually connecting source and bulk together, this issue will be of relevance, because in that case only then I know I can control Vt, and now I start doing, okay, I just ground it, or many times I do not even ground it, I actually leave it open, put a bias whatever I want there. In those cases there will be built-in VSBs or VDBs available which will modify the Vt along, and this is another issue which one has to worry about in analog design now, because this is self-bias as we call, okay, it does automatically itself. Okay. Yes. Actually this VSB is only not only on the source side, it is also on the VDB side. Depletion layer is on the both sides. The value which I am really using is the average value. Is that correct? Depletion layer is on the both sides. So Vt on the drain side is not same as Vt on the source side. Okay. The general calculation is triangular average. Okay. This is the game we play. Area of a triangle is half this into this. So same concept we use, and we say okay, average take it. But essentially equivalently saying it is increasing with self view appearing there. Earlier it was not there. Why it was not there? Because always substrate and gate were connected. Once they are connected, there is no, of course upper side there still will be there, but at least there is zero change in that, so that average will go down, so that change will not be so stronger. Now both changes can actually hurt you. Is that clear? And this hurting you means Vt will now enhance, and what is the problem if Vt enhances? Current goes down, and all that we are looking later, as we say, the transconductance is essentially a function of current. Okay, larger the current, larger is transconductance. So gain falls if Vt increases. Is that correct? Of course one advantage you may say, oh, power goes down because the current has gone down, but then if we shall see later, essentially GM goes down and bandwidth also will go down. So essentially what will happen, that all that analog was looking for probably may not be attainable. Just by not doing anything you may actually land in the situation which is not meeting your spec. The reason that you did not take care of Vt variations. In analytical sense many times we do not do this because it becomes nonlinear equations, keep solving them difficult. So we take some average value and substitute that as a constant and use it, but in SPICE you can, it can solve anything in given time, and therefore it will always be able to take care of point by point Vt variation, take averages of whatever they wish to it. So we do not have to worry too much ourselves now, but earlier this was a big issue for us. We never cared that Vt is varying too much. The reason probably was also the gammas then was very small. Now with the increased dopings, the gammas are becoming stronger, and that has pushed Vt variations. Okay, newer technologies, more problems. So it doesn't, no? Because it is a P substrate, N substrate. So upper is, it is always reverse biased. P plus is, yeah, I agreed, but there the potential, that diode, even if it conducts, what you are saying is true, is offset by this VGS value, because now they are showing some bias value equivalently putting minus there, is that, and you need a minus value to appear, so it will compensate for that. As if this bulk will go to higher potential, and which essentially will offset the upper voltage VGS value for that, okay, equivalently saying 0 here, 1 here, 1 here, 0 minus there, that is the way the voltage will look into, okay. We will come back to your issue, is very interesting. Okay, so this is one issue which we have not taken in models, now we have to take care. The second issue of interest is very important. We say that saturation parameter lambda, we said last time that it is lambda dash by L, and we describe some lambda dash value which is under root of 2n substrate or something equivalently. This is not actually numerically it is okay, but it is not dimensionally correct, so we may have to put constants which will give dimensions for that. Now this essentially we are trying to say, once we declare lambda there, then we say okay, it is constant, it does not vary with VDS. What we say, we have taken care of variations through lambda saturation, but we say that itself is constant. Is that point clear? In our derivation of this, we say okay, there is a lambda, there is a slope on the ID VDS, but that slope is constant. That is our assumption, that is if I change the VDS, the lambda does not change, but in reality that does not occur, lambda does change with this. Now why it is called, we will see this later. There are two parts in lambdas in reality. One, because of that is what we call as channel length modulation, which is lambda, from where actually this lambda dash by L appeared in fact, and the second term is called lambda m, which essentially is related to mobility. If you see our current expressions for the MOS transistor, IDS is proportional to mu. Deriving this all expressions, we took mu out in the integral out. When I calculate IDS VDS characteristics, I removed mu, I took it constant, but in reality mu varies with the electric field. Okay, mu varies with many others, but at least for us immediate worry is of the electric field. And since mu varies with the electric field, we are applying now larger voltages, larger fields, because channel length is reducing and voltage is not scaling down. So we have fields which are not small enough now. Long channel, this issue was not very strong. Why? Channel length of 1 micron, 5 micron, 3 micron, even 0.8 microns, fields were 3 volt, 3.3 volt. Now voltage is only 1.2 volt or 1.5 volt, and the channel length has gone to 65 nanometers, 45 nanometers. You can see how much fields are suddenly boosted up now. Now these fields will be affecting, because mobility is essentially the connected to how much drag it sees when it moves in the solid state or semiconductor. Essentially if the field is higher, it will get retarded because it will accelerate, it will likely to impinge next electron immediately, and therefore it will scatter faster, and therefore it will reach relatively late at the other end on an average. This is called drag. Mobility reduces as the field increases. Now this issue also now, therefore lambda m should also be a part of lambda, and therefore this new lambda must be now derived. The first one, let us see the lambda c part. If you see an expression of transistor, or rather your figure of transistor, just a minute, I will put it again that slide, but just you can see from here, as I increase VDS, which is larger than VGS minus, right now let us say VSB is not there, VSB is 0, even if it is there does not matter, but VGS minus VT is much smaller compared to VDS, and if you keep in at this point when VGS minus VT is VDS, we say it is pinched or channel does not exist at the corner drain. As you increase VDS further, the channel pinch off point shift towards source, is that correct? But in a transistor, if you look at this transistor, the actual channel length we say it from source to drain, which is channel length L. Once the pinch off point moves away, the effective channel length is not L now, because channel is existing only L minus the depletion layer here, is that correct? total length is L, but the depletion layer, rest is depletion layer, the actual effective channel length is reduced. Is that correct? If this channel length is reduced, so I must now take care that this channel length reduction must appear in my expression, because actual L is not L but it is L effective, which is L minus XD. Is that correct? And XD is now function of VDS, which means now even the channel length is a function of VDS. Is that clear? L effective is L minus XDL, XDL is a function of VDS, larger the VDS, larger is XD, therefore smaller is L effective, which means if I see the expression W by L and now I replace it by L effective, larger the VDS I create, L effective goes down, means current increases. Is that correct? The slope which you say is visible to you is essentially as VDS increases, L dash starts L effective starts reducing, so essentially current starts increasing from low value of VDS to higher value of VDS, and that is why in our transistor characteristics we did observe on an output characteristics IDS VDS for any VGS initially is linear, then we expected theoretically something like this, but what we got is this, because as VDS increase the effective channel length reduced, but that also influences the lambda itself, and that is the interesting part. This is one effect which is obvious, this is called channel length modulation. Why it is modulation? Because channel length get modulated by VDS, changed by VDS. So as VDS increases, XD increases, root of VDS, but it increases, so L effective is L minus XD, and therefore effectively effect channel length goes down as increased VDS, and therefore you keep seeing slopes. Okay. So this slope, so first thing we say saturated, so it is no more really saturated. Now ideally what do we expect to happen? We want something happen this side, because that will give me what we will see I delta IDS ratio, as we say it is an infinite value kind. If that happens I say, oh fantastic. For a current source if I want R0 I want infinite, so I would prefer saturation to a constant current, but now this is not a constant current. How much it goes away is a very important issue for me. Is that clear? And now this is what essentially related to lambda. So we look into, of course I derived it in a big way, but you need not, you can also write down, because I normally solve all expressions. So we observe that lambda c is a function of depletion layer width XDL, which is twice Ks epsilon QNA psi s plus V. Now this VSB dash is nothing but VSB plus VDS, because if there is a VSB, depletion layer is further getting enhanced from the substrate bias side. So the net substrate bias we can say is equivalent to saying VSB plus VDS. If I substitute now in my XDL expression, I say psi s plus VSB plus VDS, so larger value of this will appear, and obviously larger the VDS or larger the VSB, even if it is root, XDL will enhance, okay, XDL will enhance. I did some calculations further, I just put this as a constant, I then differentiated. I want to see how depletion layer changes with VDS from this expression. So I differentiated this expression, I got K1 this, right now it is d by dVDS. So this will become minus half, as is that clear? I am trying to figure out what is the variation or slope of XD versus VDS, because I have figured out that the current which is increasing is essentially, how do we actually put it into expression in our IDS VDS, 1 plus lambda VDS, we put some lambda parameter. Now I want to see this lambda which you thought is a constant is itself is a function of VDS, then as you increase VDS the slope may change, and if slope changes then you have more worries, where do you bias your device? Is that point clear what I am saying? Let us say for some reason, I do not know whether, let us say it is something like this, that means biasing here or biasing here will have a different R0s, which means different gains. Is that correct? So the worry is very relevant, because my ultimate aim is what? I want to get at least the minimum gain specified and minimum bandwidth specified. Okay, I must reach there. If it affects me somewhere, one, of course you can say you change the bias point, yes, but in circuits once you design, if you change bias point, many other things will change. So you may, okay, you keep somewhere, okay, here, then you see how much tolerable things you get. If not, then of course you will have to modify your bias point itself. This is how the issues are actually tackled. So I did this differential, you can do yourself, final expression you can write. This can give me, after differentiating it, XDL versus VDS, K1 prime, this other constants I took care, it is psi s plus VSB to the power half, 1 plus VDS upon psi s plus VSB to the power half. We know after pinch off, increase of VDS, increase XDL. So the L effective is L mask, that is the actual channel length you keep minus the depletion layer, and then we define the channel length related lambda as 1 upon L effective dxdl by dVDS. Is that now clear? Since this is a function of VDS, lambda is a function of VDS. Is that point clear? Since dxdl by dVDS is positive, is a value which is varying, since this is a different VDS will have different this, lambda will also vary with VDS. I did this calculations further, just note down this. L mass, please remember, when I design a chip, I have to give some dimensions for transistors. So source to drain distance we call it channel length, that is on a mask which prints. However, in real life, because of depletion, the effective channel length is not same as what I thought as channel length. Okay. Now this is function of 1 upon L effective. Please remember, this also is a function of VDS, and there is also function. So there is some plus minus, but some is increasing more, some is decreasing, and therefore there will be at every VDS, lambda C is not really a constant quantity, which I assume lambda constant. Okay. Many circuits this works without just thinking, you put it and God is on your side, so it works. But many times bad days do come and then you find your circuit is not behaving. So what you do, the best person is keep tweaking. One method is thoda hilate raho, kuch to hil jayega. At the end of the day, what happens that it may take millions years possibly to actually reach to the value, okay, or sometimes in a first hit, okay. So there is a probability, and in event probability is not known. Please remember, if I put a dice 100 times, I have no real worries, okay. Someday you say 50% head and tail, but in a time frame there is no probability. When this event will occur is not known. This can happen now or maybe after any number of years, okay. So time event is very difficult to predict. So when you say, oh, it has a very low probability, agreed, 1 in million, but that 1 in million may occur now, then what do you do? Okay. So for a worst case designer, we must know a priori what can happen worst. Then I say, okay, I will take care of this. Is that issue? Why designers look into all those issues? Because for them that worst case is what he is designing for. Heavens may not fall, but may fall. May not means may fall, and that may be today. Okay. And that is where the worries are very strong in designs. So is that clear? When I teach a course on analog circuit, second year, I keep telling nothing happens, this is how it happens, this is how you can derive. But when I start designing, I realize that my circuit is not performing as I thought, as my analysis gave me. I thought it should give me gain so much, bandwidth so much, it did not. Then I start going back and say, what went wrong? I actually followed the professor, he said this is how you should, analysis is like this, but it is not working. The working part probably is the deeper issues which we that time hardly tell, because we thought that at the concept part we should tell. But here is not just the concept, here is something, an issue which is real life, things may not work at all. Okay. But as I say, I am telling God is great, most cases it works, because you last year thesis you will pick up what values he chose, so if he has got it you will also get it. This is how it works, okay. Saath hi haath badhana. So that is how it works, but essentially it is a trick which may work, okay. So what is the designer's expertise is, he should have therefore experience. If he has done 10 chips, 11th he knows very well what goes wrong when, okay. So he takes care of that, okay. That is why I keep saying analog designers have to be experienced design, because he must have seen many failures. He knows what goes wrong. So then he has a thumb rule, oh aisa hai to aisa, aisa hai to aisa, okay. That's what exactly, therefore it is more of a art rather than science, because that art is assuming you have enough science in you, okay. That's why you figured out this is how empirically it is working. But to get that empirical relations, you must understand why this is occurring like this. This is what all that I am trying to hit, okay. So if you look at the IDS characteristics once again, half beta dash WL effective, this is what I said. So L effective is L minus XDL, which is, if I modified this, I substitute and I see this lambda C, which is something like this, is now a function of VDS through XDL and also a function through DXDL by this. I do not want to expand all of it, though if you wish I can show you the kind of expression which I derived, seems to be very funny. This is the expression, just note down. These are nothing great. This is IDS is some original expression. Now can you think I did some mischief here also, that lambda part is really taken care through this L effective part. Is that correct? I did not put 1 plus lambda way, but I am taking care through L effective, that issue. So if I solve this, I just put x minus this as this form, I get this expression. And once you get this expression, you do not have to write, you write down my final expression. I only took time to write down all of it. So lambda C is L minus XDL upon this, and I hope you have written down. I have got both expression, every expression I have derived, XDL I have derived, DXDL by DV I have derived. I just now substituted this. Is that okay? Just substitute, and if I substitute, is that okay? The lambda C, I will come back to it. Lambda C, oh maybe you write down the last, this is not, this anyway we are not going to solve by this way, this is only to show how SPICE will take care of many such issues, okay. Lambda C, we said lambda dash by L, is that correct? So I actually converted into that lambda dash by L kind of expression by substituting, this is L effective kind, this is my DXDL by DVDS, just substituting, and you expand this, and this is the kind of expression you get it. What is this expression? This is that lambda dash term which I said lambda dash by L, and this lambda dash is a function of VSB, function of PDS, and therefore lambda is not a constant quantity. Is that clear to you? Lambda is not a constant quantity. Okay, so you may note down, then I will show you the second part of lambda. So you can see from here lot much expressions appear, okay. So now this issue is clear that 1 plus lambda VDS, lambda is not a constant, though as I say in all our analytical designs we will assume some value and get away. But reality must be in your mind that in real circuit sometimes Y circuit is not performing, partially maybe your R0 is not getting what you are thought, okay. So what is the solution? You use VSB as additional feature for you, okay. You have VDS VSB, you actually play with VSB then, okay, and adjust that value so that you get R0 of your choice. Is that clear to you? This is what I am saying, design. Additional VSB is in your hand. Now earlier we never did it, now we have a control, okay, I will play with it, okay, to get what R0 I was looking for. This is the trick which I thought you should know why people actually go and bias it then. Now there are issues further, do we need constantly bias? We may not. So there must be some feedback somewhere which says when I want and when I do not want, so that removal of VSB also should be possible. So that is more complications. Is that okay, all of you? The second issue in the lambda was related to lambda m, which is, as I say, mobility dependent. We do not go into too detail because it is much more interesting from the device point of view. how mobility varies, why it varies, you just take it from me that this is the expression which is mu 0 minus mu VDS upon mu 0 VDD. This is called the lambda parameter with mobility variations, where mu 0 is the low field mobility and mu VDS is the mobility at the applied bias. So if I now assume that lambda c is varying for a given bias point for a given VSB, I still assume lambda is lambda c plus lambda m is still constant, which may not be true, but okay. And if I use this expression, this is the expression which I got earlier to show, that is what the model, why I showed you now fully model, because in real life model and in the analytical model what is different. We assume this constant which was not there. In beta dash we assume constant which was not. Okay. So when SPICE does it, it does not know anything. You are given some physics to it, it actually starts solving, and then your value of IDS is not same as what you thought analytically. Is that? But why do you need analytically then? Because which value to start the simulation? So initial guess तो चाहिए ना. एक non-linear equation है, यदि आप guess गलत कर दें, so there is no possibility of you reaching the solution because it is already divergence. Okay, you have already caused fx0 function. So in solution it is very essential for a nonlinear system to know initial guess and guess very closely correct. Okay, analytical solutions do give that guess actually. At the end something CAD will work, but where to where, otherwise it will take some, like for example Intel Pentium 4 chip, the latest version, actually took, in the first time they did 6 months of simulation on that. So many transistors, so many, this hardcore problem was, a lot of good computer scientists were there to do parallel process, everything, and it took 6 months to finally get through. Okay, because they wanted full test for that. They did. Now they don't know. Now they know how much is important, how much, that much simulation is enough for further designs. So some analytical thinking is an essential part in analog designs. Okay, so if I use this expression as it is, this is the expression without VDS and this is the expression with VDS, and if I plot for different VGS, IDS characteristics, at least the lower side of the IDS VDS from the knee side, if I extrapolate them down to minus VDS axis, this is for N channel device. Okay, for P channel it is the opposite side. Actually where it will come? Third quadrant. This is in the first quadrant, this curve will be in the third quadrant and this PA will be positive there because this will be the other side. Please remember it is minus VGS minus IDS for P channel plus IDS plus VDS for N channel. So just take it to the third quadrant and you will find that is for P channels. So if you see this expression, if you see this equation, all of them somehow meet at a fixed value of VA. Is that correct? The slope is 1 plus lambda VDS, VDS term you are taking. This is, so I figured out that if I take this as a VA, this is equivalent saying lambda must be 1 upon VA, because then only it will mean that if you assume lambda is constant and at this point yes I had VDS, it may not be. So this is called early voltage, this is called early voltage. So many a times instead of specifying lambda they may specify you early voltage, which essentially is giving you lambda indirectly, okay, or 1 upon VA is lambda. So many problems when I give or intentionally I do otherwise, I say okay early voltage is so much, okay. So that essentially is giving you the slope characteristics. How do you calculate? You can see if this is the current and let us say this voltage is very large compared to this, let us say this is 50 volt, this is 0.5 volt or something. So assume that is smaller. So this is 50 volt divided by this much current is the resistance, is that correct? So what is R0? This divided by the bias current which you put is roughly R0 for it, for you, is that correct? So that is the analytically solution, how much R0 I am getting, I can see directly from this expression itself or this curve itself. I repeat, VA is called early voltage, the word has taken from base PNP, is a bipolar transistor when the base gets punched, okay. the depletion layer from base collector junction goes to emitter junction, short circuit equivalent occurs, and at that time we say there is no transit time, all carriers can go, okay. So that is the point at which we say punch through has occurred. Let us revisit the Vt expression once again. We are also interested to know delta Vt is this expression, and we like to see if Vt varies, how IDS varies, because if you say VGS minus Vt and Vt varies, then I must know what IDS varies with substrate bias, because if VSB changes Vt, IDS will also change with VSB. So I want to know relationship between IDS and substrate bias, because these are all issues analytically I may brush aside, but in real life they must be taken care in solutions. Is that the issues which I am raising are first order issues? There are many second order effects which I am not talking about. There are many issues right now, but at least the dominant issues must be brought for the designer, because this must be understood that why your specs sometimes do not meet. The reason you are not taken care of many of such smaller variations, you thought smaller, but they are no more smaller now, okay. So I want to know relationship between this, okay. Also in many books and many times I also, this VSB and VBS is interchanged, but take it is only minus, okay. Sometimes you write bulk to source bias, sometimes you write source to bulk bias, okay. If it is so, just change the sign, because source is grounded, so the VSB should be minus, but I can assume this grounded and plus Vs I can create equivalently. So which way I look at the bulk and which way I look at the bias is only your choice. I say VBS, you may say VSB. So the bias is same, do whichever way you look, okay. So this sign has to be taken care whenever, sometimes in some books you may say write VSB, some other books they write VBS, and then they do not show you sign. The sign has been taken care through opposite polarity here. So please take it, because this the 2 or 3 books which I suggested, they all are not agreeing with same nomenclatures. So I thought in case some of you will read the book, hopefully in that case if you have an issue then you can get rid of. Okay, I did this. Please take it, this is very important and this is needed immediately for us. Why I brought this? Please take it, this expression is going to be used in my actual equivalent circuit, that is why I thought I should show you immediately. So I write IDS is beta VGS 1 plus this, sorry that half part somewhere I think I missed. Then I differentiate this, and of course then 2 also will go, okay, just check it, I think there is some, I did it, that is terms constant use check for this. So I differentiate this, I have already calculated this earlier, delta Vt by delta Vsb, which last expression I have shown you, substitute here and I get, okay, maybe this 2 may not be there, beta times Vgs minus, just check it that whether 2 exists, because I have not taken from, I just saw it few minutes, 1 hour ago or something. So it is beta times Vgs minus Vt plus this constant gamma upon 2 Vsb plus 2 phi f to the power half. I think that 2 has been taken care by me somewhere, I just do not take it, but just think of it. This is a constant. For a given VSB, gamma is already only a function of Cox and dopings, this is only a function of doping. So eta is some constant you have, and what eta represents? What is the eta's importance? It takes care of what? Vt variation with substrate bias, okay. You are worried about now that if substrate bias indirectly also appears, Vt is going to be affected. So what we do is, this of course we can equivalent to saying that eta, this is of course we will see later Gm, okay. This eta is given by this expression and typically this is 0.6. Typically eta has a value of, typically does not mean actually, you may have to solve for given values, but around 0.6 is the value. And we will prove little later that this term is Gm, so this delta IDS by delta VSB, what name I can give you? It is also GM, but with bulk substrate, so I say GMB transconductance for the substrate bias is equal to GM times eta. We will prove this is GM, but abhi, okay. So we say not only there is one GM going on with you, but there is an additional GM is created if there is a substrate bias, and which is not small. 0.6 means if they are in parallel GM sources, then it is 1.6 GM equivalently I am going to get, equivalent current source. So you thought it is smaller, but it is now higher, okay. That is why I say VSB is now my parameter of control. I said look, I can now start playing games on it, is that clear? That is why I showed you first time, maybe I am telling you that why VSB became so relevant both in digital and in analog, because now the technologies allow you to do many other things, okay. Okay, so this GMB is another parameter of new designs which you must take care. If you have a MOS amplifier and right now this load is RD, I start looking at that the input Vin is V bias plus V signal. So change in delta Vin, which is signal, is Vin minus V bias. We always define small ID capital DS is equal to small IDS, which is the AC current or varying current, time varying, and this is DC. This is how small signal values are expanded. Delta IDS is the AC current, okay. So if I bias, this is my MOS VO for an amplifier VO-VI characteristics, and let us say I bias at one V bias, that is on the Vin side. I fix the bias VGS, whatever I fixed here, and then correspondingly I know some V0 I am going to get because of the transfer, okay. However, if you see delta IDS by delta Vin, that is delta IDS by AC this is small IDS, this is small VGS, which is nothing but the transconductance. So now I see delta V0 change in, if there is a small change in bias to this, there is a change in V0 from here to here, that delta V0 is minus GM times R into, this is the current, delta IDS into R, delta IDS is the AC current, R is the voltage drop across this, so this is the Y minus, no, that is the part. From here, it is actually, if you say total value VDS minus IDRD is this, but DC for AC valuation DC goes away, so minus IR is the output AC voltage. This occurs because of what? The transistor always gives you 180 degree out of phase currents, okay, out of phase to the input 180. Minus can be thought as J square, J is 90 degree, J square means 180 degree. So it actually gives you opposite polarity whatever is the input side, and that is something this is what the principle of inverter was in digital. Same way here is only difference we will call now is it is out of phase, 180 degree out of phase. This is very relevant in all analog designs, how much phase you create, okay. Okay, so gain function from this delta IDS by delta VC GM, so we are substitute here delta V0 by delta VGS is minus GM R, and this is essentially the gain of a amplifier. Sorry, this is RD, so please change it to RD wherever I had done it, okay. However, as I said to you, in real life RD may not be the one which I am going to use in fact, okay, because resistance, just for the heck of it, for those who think otherwise, if you don't note it down then I will just show you why I never like to use actual resistors in silicon, okay. Though I can create, I will show you what I can create, but in some circuits even in analog you are forced to use resistances. Which block of the circuit normally will use this, anyone, any heard of it? जो थोड़ा सा सेकेंड ईयर में आए हैं. The band gap reference, when I create fixed bias, that time there will be R requirement, because I want temperature, positive temperature coefficient something. Transistors give negative temperature coefficients. So I need compensations. So I actually want positive temperature coefficient material, R is. So I actually put R there to compensate. Okay. So think of it, R is not completely out of picture, but in most circuits will not like to use R for this reason. Typically semiconductor bar, if you use it, and this is the current path, I ground this, I apply VDS or V. So V is equal to, so current I is entered, so V by I is R. But if the shape I intentionally chosen, R can be always written as rho L by A. This is my length, this is my T, and this is my W. Okay. So this rho is called resistivity of the material. So rho L W into T. So that is called R is equal to RS L by W, where RS is called sheet resistance or sheet resistivity, either of them, which is rho by T. For a given technology, generally this available, because we are not going to put separately, whatever processes we have for making CMOS, only those dopings will be available to you, wells, substrate, N plus, P plus, those are the only areas available. This value is normally given by the word which is called sheet resistance or sheet resistivity, is always technology dependent, what process you are doing. And the highest RS which I can get in a normal technology, normal, I can create, which is ohm per square, it is defined as ohm per square, 200 ohm per square, that is the best I can get. Of course, other materials can give mega ohms or mega ohm per square, but silicon process technology for CMOS will not allow you a region which is better than 200 ohm per square. If I want a 40k resistor R, from this expression how much will be L by W? The highest I have 200 ohm per square. How much it is? 200. This L by W is called aspect ratio. Is that correct? Aspect ratio. L is 200 times the width. Length is so much and width is so much. Any drawing person will tell you that if the aspect ratios are, the accuracy in making that itself goes away. Because I cannot hold on that 1 micron line for 200 micron. It is very difficult by drawing also. But even if I print otherwise, the problem is, if let us say W is half a micron for a given technology, half micron technology, this is 100 microns. So in a transistor may require 0.5 by 0.5 micron area, and your resistor is requiring 200 into 0.5 area, और एक resistor, अभी इतना सब जगह लगाएंगे, so transistor दिखेंगे नहीं, सिर्फ resistor ही दिखेंगे. थोड़ी देर बाद पता लगा कि chip size में 4 resistor के बाद कुछ जगह ही नहीं है. So इसलिए one cannot use resistors because it will just take away your area. Of course you can build this if you can increase this rho RS to 1000, 2000, 5000 polyresistors people use sometimes in DRAM, SRAMs, then there is a special technology, additional money. If you invest, yes, R can be reduced, length width ratio can be reduced. So in most technologies what we will do is, we will use transistor itself as the resistor. You can see from here, after ID VDS means current voltage. Slope of delta V by delta I is a resistor. So there is a small resistor here, there is a large resistor here. So you keep your transistor either in this region or in this region. So you either get this resistor or you get this resistor. To change this, change the W bias, because IDS is in your hand, W bias. So change the size and you get different R's, is that correct? So in a analog circuit, preferably transistors will be used as resistors, they will never be used as, I mean there is no additional such huge, of course one to save some area, what do, anyone? No. So how do I do it? Spiral it or meander it, okay, something like this. So थोड़ा perimeter adjust कर सकते हैं, but area जाएगा ये, okay? You can adjust bit of perimeters, okay. Okay, so is that issue why R's are never, so in though in circuit classes second day earlier hai, we keep showing R there, okay, because it's okay, it doesn't matter how do I create, but I just want to put the numbers there. But in ICs, the first thing we'll do is we'll get rid of this actual resistor from there. Now the problem with this, most cases when I put some transistor there, I must guarantee that that R doesn't change, okay, and if that changes then I have more problems, and that is where the design starts, that okay, that R is not really the constant I thought, okay, it varies, then how much varies, so can I take care of my design so much very, okay, this is the issues which designers look for. Now I do a same expression again 3-4 times to show you some other way of looking the same thing. I have that same VCCS IDS kind of amplifier shown. I rewrite the expression delta V out, which is AC in fact, half beta VOV square, right now I am leaving alpha, minus half, not alpha, lambda, half beta VOV plus delta V in, VGS minus VT minus plus V small this square, call this, okay, here I have used R. So I expand squares, remove the terms if they are there, VOV square and this will go away, okay, and I get delta V in square plus 2 VOV delta V in. This VOV cancels. So I get minus half beta R 2 VOV delta V in into 1 plus, just adjust the terms, there is nothing big going on, I just take out some terms, leave some terms, okay, inside, just take VOV V in out, so I get 1 plus, I am taking this whole expression out, so 1 plus delta V in upon 2 VOV, okay. Now this expression can be further modified, have you written down? Please note down. I repeat, what did I do? AC is nothing but total minus, this is with signal, this is without AC signal, so subtraction is only due to the AC signal, okay. I am now going to get another GM expression which is very relevant, and that is what designers should look at, that is why I brought these expressions for you. Expand this, VOV square delta V in square plus 2 VOV, minus I took sign, so this minus VOV cancels, square cancels, so this, I take this term out, so I get this term. Is that okay? Okay, is that okay? Everyone? Minus half beta R 2 VOV delta V in 1 plus delta V in by 2 VOV. Same expression, just adjust it. What is this half VOV square? Half beta VOV square is what? DC value of IDS without signal, that is what VOV square we started with. So this is IDS, 2 delta V in R by VOV plus delta V in by 2 VOV. This becomes 2 IDS by VOV. Is that clear? 2 IDS by VOV. The remainder term is R delta V in into this. Is that okay? Only reorganizing the terms. Nothing great I am doing, I am just reorganizing, because at the end I am looking for the delta IDS, I mean IDS by VOV term at the end. So I get 2 IDS by VOVs are, this delta V in is delta V in, 1 plus delta V in by 2 VOV. Now what is the gain I defined? AC voltage by AC current or change in output voltage by change in input voltage, which from this expression becomes minus 2 IDS by VOV times R into 1 delta V in by 2 VOV. Is that clear? If you say it is a small signal, AC signal, delta V in is much smaller than VOV, because what is VOV? Capital VGS minus VT. VGS is the bias value, volts. What will be signals? Millivolts. So you can see there, as long as that is the condition I am putting. What is small signal? Gain must be very small compared to VOV. Is that correct? Then it is small signal. In that case, this term can be neglected. So I get minus 2 IDS by VOV into R, but I know AV I just derived as minus GM times R, okay, which means the GM is 2 IDS by VOV. Is that correct? This is an expression which I will use. This is one way of looking at the design using this is my parameter. I want to adjust GM. I will adjust GM through 2 IDS by VOV ratio. Is that correct? I am going to adjust my GM through ratio, neither IDS nor VOV. I can do either and do this, but what I am now given you, I take the ratio. So now I have a larger game to play. I change sufficiently both, okay, some way, so that I get a ratio, and to adjust to this I will adjust W by L, so that this ratio is different, but individual is different, but ratio is what I am looking for. This is called IDS by VOV designs. This is different from VOV designs. Everyone used to always design using VGS minus VT. Now I am introducing a new way. Say, okay, let's look design based on ratios of IDS to VOV. Just don't look for VOV alone, okay. I will show you there are 3 possibilities which can, one of them is this, and this is much more powerful tool in actual designs. We can always design bias dependent. Here is a ratio of, so GM dependence is what, because GM, why I looked into this kind of game, because at the end of the day, what is my important parameter for gain? GM. So I say, okay, you want this gain, so you want this GM. So let's go back and look what can I do for this. Okay. So I am now looking more from the analog side. Okay, GM control chahiye. So what should I control? As long as I adjust the ratio, I need, because then the issue started. Power will come, everything else will come. So I see to it that all this adjusts to this. Okay. I don't say this should be 10 and something, I may say 100 and something, I may say 5 and something. I have a ratio to adjust. Is that clear? As long as that ratio adjusts, I get my GM. Okay, so this is essentially, I won't say very new method, but this is little better techniques of designing a chip rather than the normal VGS VT minus method, which will show you that is also possible. Initially you may solve using those methods, but then I show, okay, now convert on this, you have a variety of solutions. Now before I go to the next gain function, I have not yet talked about that word again, but let me be very clear on that. If you see a IDS VDS characteristics in saturation, this is my ideal and this is my real. Though the slope, as I say, may not be constant, but for a one VDS I may say it is one value. Now I define R0 as delta IDS by delta VDS, slope of this characteristics. R0 is finite in real case because there is a slope, and IDS is a function of VDS in such. That is what 1 plus lambda VDS term we derived. Okay. So if I do this, there are few things which you should remember, and that is why I am showing you all this. This is a simple characteristics for R0. Please remember, we will never go in this region which is the linear region. Why? Why will never operate our amplifier here? There is no gain there, okay? There is no GMs there actually. So don't, we will always operate in saturation region, and please remember there the actual value of input available to you is very, very small because it sharply falls B0 gain. So the gain is only available in a very small gain ranges. Okay, is that expression clear? R0 is nothing but 1 upon R0 is delta IDS at any VGS. This is one VGS value. So at different VGS, this will be different, because if you have a characteristic somewhere here, this slope may not be parallel exactly, okay, and therefore they may have different R0s. Okay, is that okay? So if I write this expression IDS, again as I wrote earlier, beta by 2 VGS minus VT 1 plus lambda VDS, lambda we are now know what it is. So you must take from me now so called channel length and mobility modulation we do. In reality lambda is a fudge factor. What is fudge factor means? It is a fitting function which fits to the curve. Expression of R. Why do I want to expression? I know it may vary, so I figured it out how it will vary. In real life what we will do therefore, having found IDS VDS characteristics for different VGS at bias points, I will actually fit a curve there, okay, and get R0 there, and that is the end of it. Whether it fits into my physics or not irrespective, but that value is available to me, I will use that. Therefore, it is some kind of a fit function which I am going to use in real life. So, please remember the theory etc. is fantastic to understand, but in real life we always use this as a fudge factor fit. Okay. Now, if you do so, one can see lambda is some way related from this expression to 2 IDS beta V square upon VDS, and if I differentiate delta IDS by delta VDS, please remember this is the expression which I am going to use where lambda is given by this. I will just come back and show you the same expression which I derived earlier. Have you written down? R0 is just, there is nothing to write, only thing is statement I am making is it's a fit function rather than the real physics behind in real life. If I differentiate this, R0 is coming something like this, and if I fit correctly I get expression IDS lambda 1 minus lambda VDS. If I expand, this is roughly equal to I, if lambda is smaller, lambda square is even smaller. So it is IDS lambda. So in all expression what do I do is R0 is 1 upon IDS lambda. So if I am specified lambda or VA, I have knowledge of my R0. Is that correct? How do I get R0? Either I will be specify lambda value or I will specify early voltage which is doing the same, and then if I know my bias current IDS, then I know my R0. This is with all these conditions, so inaccuracy is partly built up, but this is the first trial for the system, so that is good enough value for your evaluations. So I always start in analytically saying that R0 is IDS upon lambda. Though I say I have shown you so much physics, how much it varies and why it will vary. Yes, our modeling in SPICE should take care, okay. But analytically this is a good enough expression for us. Is that difference clear to you? Why I show you both sides? Because you should not say that this is always correct. This is not correct, but this is good enough for analytical solutions. So first guess how much value gains will be. Let us say if you design with all these inaccuracies, your gain gets 9,900. In real life it may get 8,500, but you say it should be more than 8,000, so it does not matter whether I reach 9,000 or 8,500, okay. So how much inaccuracy I can build and is still tolerable for me is all that designer should know, okay. If that happens, he says thank you. So this is the game. Is that Raj clear? That it is not the value which matters, it is the value bound matters, and as long as we remain in the bound, your design may still work, okay. Sometimes it may call over design, sometimes maybe underachievement, it is okay, but it works, okay. Okay. So for a designer should note the following, this is my as a designer help, okay. You write down, as a designer you must know this, okay. For R0 evaluation is tentative, okay. It depends on technology parameters, it depends on the operating point, it depends on output swings, because whether that VDS is other end or this side is and how much is signal. R0 is therefore showing non-linear behaviors. I will give you some hints on that. I will show you what I meant by this swings. Use proper bounds in SPICE. Is that clear? So that is the marker. So what you should do? Use proper bounds. Okay. There is nothing called correctness. Okay. I will just show you this part non-linear how it works. Okay, just let me finish few minutes. That is the last of it. You have just now said R0 may actually, maybe I will draw a fresh figure, at different VDS something like this. This is my IDS VDS. Okay. So depends on if you are biasing here or biasing here, slopes here, slopes here, slopes here are not same. Is that correct? Even if you bias here and if your swing is something like this, large swings, even then you are hitting different R0s, okay. So there is a non-linearity built in your R0 itself, and in real life therefore it should be taken care that which value you are using which is sufficiently okay, sufficiently okay. So please take it R0 is not really a I just told you lambda is not a constant, so his R0 is not a constant quantity. So where do you bias, how much swings you give, that may decide the variation in R0, and therefore the gains will vary, every other bandwidth will vary correspondingly. See you tomorrow, that is Tuesday, Wednesday next.